Okay, good evening. John D'Alessio. Welcome to week 3 tutorial, mass and heat balance for primary production of steel. It's 8 o'clock, so we'll get started. So, some comments I received last week, one of which being Todd, who's not really an expert in steelmaking. He's the administrator of this program. He asked me, why, John? Why are we going back to the basic chemistry? I think we need to make a connection as to why we're doing that and how it goes and how it connects to steelmaking. And I thought that was an absolute question. I thought that was fair, and with all due respect, I totally agree with him. So I want to spend some time and just answer that that one question. Okay, so week 1, we started off the course. In fact, we started off the program by introducing an overview of the steel industry. What nations are making the steel, how much, what processes are being used out there, EAF versus blast furnaces, and all that great discussions that we saw in week 1. Then we jump into week 2, and suddenly we find ourselves talking about the finest particles that is known to man, the smallest particles being the electron and neutrons and protons, and how they develop and produce what we know as atoms, and how atoms form molecules, and molecules form compounds, and taking it from there to Avogadro's number about the mole, and why we deal with the mole. So why are we doing this? And the reason behind it is because these processes that we're going to be talking about, and not just in this course, but in the next 5 courses, these steelmaking processes are very predictable. And they're predictable because of the scientific laws and understanding that has been developed over the years by great scientists. So that's very important, because if we have a sound understanding of the basic fundamentals such as chemistry and physics, we can predict the output of the process if we change or make changes to the inputs of a process. And that is why we're doing it. And it's all going to emerge this evening and into next week's lecture and topic, which is the blast furnace process and the chemistry and the reactions that take place in that process. But essentially what we're going to emerge onto this evening is mass and heat balance. And to be able to do a mass and a heat balance, right, one must really understand the basic chemistry that's involved and the science of thermodynamics to understand the amount of energy that's in the system. Because what it comes down to is, by making changes on the inputs, such as how much energy we're going to pump into a process, or how much raw materials, or what type of raw materials we're going to put in, the type of chemistry of the raw materials, whatever inputs is required, whatever changes are made to those inputs is going to affect the output. And engineers or metallurgists or practitioners, right, need to predict the output so that they can control the quality, the amount of the steel, ultimately, that is going to come out from these processes. So that is why we're doing it. And I hope that is a quick synopsis and a good understanding as to why we took you back to a very basic review of chemistry. So last week we reviewed some topics of chemistry, such as the atom, the moles, Avogadro's number, and how they're applied, the periodic table, and what we extract from the periodic table, mainly being the atomic weight. And this week we're going to further that discussions on talking about gas phases, multiple phases, and how we deal with that in chemical reactions, ultimately to be able to do a mass and heat balance. So review your courseware notes, please, on this subject. There's some good examples in the courseware notes. And there's tables that you're going to need to get thermodynamic data from to be able to do some of these mass and heat balance examples that we'll take up this evening. So without further ado, we'll get started. So just a quick agenda of what we're going to talk about this evening. I thought it will be a good idea to quickly review Quiz 2, go through the questions and answers, and then jump right into the lecture of this week, which is going to focus on three main elements: gas phase, thermodynamics, and the thermodynamic tables that come from thermodynamics that we could use to actually do practical mass and energy balances. And then take up three problem exercises, which I believe have been issued, and you should have those questions for this evening. Then I thought perhaps we could leave the questions until the end and answer some questions. So on the first question of the quiz, you may recall, it was a matchup game. There was a list of reactions and a description of those reactions, and you were to match up what description applies to what reaction. So on the first one, CH4, which is methane, it reacts with oxygen, and it's a combustion reaction, and the products are carbon monoxide and hydrogen gas. The fact that the product is carbon monoxide is a partial combustion. If it was full combustion, then the product would be carbon dioxide. But in this case, it's carbon monoxide. So clearly the description of that reaction would be partial combustion of methane to carbon molecules, or to carbon monoxide by oxygen. Second reaction is Fe2O3 reacts with carbon monoxide to metallic iron and produce a CO2 gas. So that's hematite. Fe2O3 is the highest oxidation of iron, and it's hematite, and that goes to pure iron by carbon monoxide. FeO is the lowest oxidation state of iron oxide. It's wustite. So it's FeO plus H2. It's being reduced. It's a reduction reaction. Being reduced by hydrogen gas, and it's producing metallic iron and H2O. So in that case there, wustite reduced to pure iron by hydrogen. And likewise, Fe3O4 plus CO goes to 3FeO plus CO2, and that's a magnetite reduction to wustite by carbon monoxide. Silicon dioxide, or silica, is getting reduced. It's reacting with carbon to produce silicon metal and CO. That's a silicon reduction reaction. Phosphorus pentoxide, that's P2O5. It is going through a reduction reaction. It reacts with carbon, and it produces phosphorus and carbon monoxide. So that's a phosphorus reduction reaction. The next one is Fe2O3 plus CO goes to Fe3O4 plus CO2. That's a hematite reduction to magnetite by carbon monoxide. Now there was an error. Some of you may have noticed there was an error on the auto grading on this question here, because the five reactions that some students were given, this reaction here, Fe2O3 plus CO goes to Fe3O4 plus CO2, could actually apply this hematite reduction to magnetite applies to that reaction, as well to the reaction above, the second reaction where Fe2O3 reacts with carbon monoxide to form Fe and CO2. And it also applies to the fourth reaction down, where you got Fe2O3 plus H2 goes to Fe3O4 plus H2O. One is using hydrogen as the reducing agent, whereas this reaction is using carbon monoxide. The fact that hematite reduction to magnetite doesn't state precisely what reductant is being used, that comment can apply to both. And the system wasn't equipped to be able to answer both answers, so I manually went in and I made sure that you were granted marks were corrected. Okay, the second last reaction, carbon plus CO2 going to CO, that's the oxidation of carbon by carbon dioxide. That's another means of which carbon can get oxidized. Carbon can get oxidized by by oxygen. So carbon reacts with the oxygen, so it's a combustion reaction to form either CO or CO2. And this reaction, where carbon reacts with CO2, is also a means of oxidizing carbon, and it's also known as solution loss reaction, which we'll talk about next week, or the Brudard reaction, also known as the endothermic gasification carbon, which we'll talk about next week as well. And the name endothermic meaning that this reaction, carbon plus CO2 going to CO, the solution loss reaction, is a very endothermic reaction, and it needs to be controlled in a blast furnace. This is going to be the main subject for next week's discussion. The last reaction is a water-gas shift reaction. It's carbon reacts with H2O to form carbon dioxide and hydrogen. So those are the answers to the first question. Questions 2, 3, and 4, there was all these possibilities, and they were randomized on the auto assessing. And so how many grams does a silicon atom weigh? Okay, so most of you just some of you just stated the molar mass. Well, that's not correct. It's the molar mass divided by Avogadro's number, and that would be the mass of a single silicon atom. So that in this case would be 28 divided by 6.02 times 10 to the 23. The second question, how many grams does a silicon oxide or an SiO2 molecule weigh? Well, the molar mass of that molecule is 60. Oh, excuse me. On the first one, how many grams does a silicon atom weigh? The answer to that would be 28. So the molar mass of silicon is 28 divided by Avogadro's number. Second question, how many grams does a silicon dioxide molecule weigh? Well, the molecular mass of SiO2 would be 28 for the silicon, 32 for the 2 oxygen, which gives you 60. Divide that by Avogadro's number, which is 6.022 times 10 to the 23. The third question, how many atoms are contained in 1 mole of silicon? Well, that would just be Avogadro's number. Whether if it's atoms or molecules, getting down to the next question, how many molecules in 1 mole of silica, SiO2, that too would be Avogadro's number, 6.02 times 10 to the 23. So a mass of 1 mole of silicon is the atomic weight, or the molar mass, which in the case for silicon is 28. What is the mass of 1 mole of SiO2? Well, that would be 60. So those are the answers for the second part of the quiz. So let's move on to this week's lecture. We'll talk a little bit about gas phase. Okay, so let's start off by asking the question. So how do we quantify the amount of molecules and elements of different phases involved in a chemical reactions? Well, what is meant by that is common examples: sugar dissolved in water, salt dissolved in water, which you give brine. More so in a blast furnace examples, we're dealing with hot metal, which has carbon dissolved in hot metal, like sugar dissolved in water. And in this case, carbon in hot metal typically is about 4.5% weight carbon. Silicon as well is dissolved in liquid iron at about 0.5% silicon, and likewise with sulfur. So here we have multiple phases. We have iron in the liquid phase, and we have dissolved species. So how do we, and in some cases, and in many cases in fact, we have the gas phase. So how do we quantify the amounts of these phases when we have multiple phases in a reaction? Okay, so how do we measure volumes of reactants and products? In this reaction, as an example, we have carbon solid. It reacts with oxygen gas, and it produces carbon dioxide gas. Now going back, and one of the reasons why we discussed Avogadro's number will come very clear in this lecture, is on a molar basis for this example. Okay, we have 12 grams of carbon solid. It's going to react with 32 grams of oxygen gas, and it's going to produce 44 grams of CO2 gas. So the answer is the mass of a solid substance we're going to measure in grams or kilograms, and the volume of gases or gases in general, we're going to measure their volume in units of liters or cubic meters, depending on the question that's being asked and the scale of that question. So Avogadro's number from week 2, we learned that a mole of a compound have the same number of molecules as any other substances. So for example, if we have a mole of say carbon atoms, right? Well, that's going to be this, and we have a mole of silicon atoms, they're going to have this the same number of atoms, independent of what element it is. Well, further to Avogadro's work and how it links now to gas phases and becomes very helpful for us to be able to do mass balances is 1 liter of hydrogen gas and 1 liter of oxygen gas at the same pressure and temperature will exhibit the same number of molecules. So with that fact, we're able to predict and we're able to measure quantities of volume. Now moving on to Charles' law. Charles' law states that as temperature increases, the gas will want to expand, so therefore its volume is going to expand. So the volume is proportional to the temperature. So what does this tell us? Well, the volume of a mole of gas is 22.4 liters at standard temperature and pressure. So on this linear graph, where volume is proportional to temperature, at a temperature of 273 kelvins, which is 0 degrees C, right? Most ideal gases will, at standard conditions, will occupy 22.4 liters of volume of gas for 1 mole. Standard conditions is defined as standard temperature of 0 degrees C or 273 kelvins with a standard pressure of 101 kilopascals or 1 atmospheric pressure. So, Boyle's law. At a constant temperature, a fixed weight of gas occupies a volume inversely proportional to the pressure exerted on it. So what does that mean? Well, it's saying that the volume is inversely proportional to the pressure. So if you take a volume of gas and you were to compress it or increase the pressure, and because you're compressing it, the volume at which it's occupying is going to decrease. So now you're packing in all those molecules and the pressure will increase. So that is why the volume is inversely proportional to the pressure. So if pressure is doubled, then the volume is halved. And likewise, if the pressure is halved, then the volume is doubled. Further to Boyle's law is if you were to take 2 different gases, or actually it could be the same gas, and have them in 2 separate containers, and the first gas is at pressure 1 and volume 1, and the second gas is at pressure 2 and volume 2, then its respective multiple of pressure times volume would equal to a constant. And why is this important? Is because what we've talked about, Charles' law and Boyle's law, puts the ideal gas equation into perspective. And this ideal gas equation is an equation that we could predict pressure volume, and temperature of gases, where PV is equal to nRT. And P is the pressure, and it's measured in atmospheres. Volume is, V is the volume, and it's measured in liters. N is the number of moles. And R is the gas constant, the number that we use. There's many numbers for the gas constant, but the gas constant to be used for this equation, the ideal gas law, is 0.08205, and the units is liter atoms per Kelvin mole. And T is the absolute temperature in degrees Kelvin, where 273 Kelvin is equal to 0 degrees C. So 1 Celsius degree equals to 1 Kelvin degree, and when working in Celsius, you simply add 273 degrees to convert to Kelvin. So we'll revisit the gas phase laws when we take up some examples. So thermodynamics, what is it? What is thermodynamics? Well, it's a science. It's a science that deals with transformation of energy. So why is this important to us, and why are we talking about this in the metallurgy program? It's simply by taking a look at those two pictures down below. You can see in the skimming operation on the left, you're skimming steel, and on the right is steel ladle and movement of some sort, I would imagine. But you can see the enormous amount of energy that's being expelled from these processes. So in order to predict how much energy is going to come out, how much energy is required to be put in, a solid understanding of thermodynamics to be able to quantify energy, as we see energy being very enormous in these processes, is definitely paramount. And that is why some level of understanding is required. So what is energy? Well, energy is defined as the capacity to do work. And it's simply the force that is applied multiplied by the distance of which it's traveled. And the unit that is typically used to measure energy is in joules. So 1 joule is equal to 1 Newton force times 1 meter, whereas 1 Newton is equal to 1 kilogram multiplied by meter per seconds cubed. So it's mass times acceleration. So in this case, 1 Newton is equal to 1 kilogram meter per second squared. So what does this mean from a conceptual sense? Well, picture an apple, okay? Picture an apple, somewhat of a large apple, weighing 1 kilogram. So by taking that 1 kilogram mass of apple from rest at being still, and applying a force to it to displace that apple from a speed of 0, right? And in 1 second you move it 1 meter, you would have put 1 joule of work into moving that apple. That's another way to kind of perceive it. From a chemical sense, every chemical reaction is accompanied by some energy change. For example, as we all have seen, campfire. We love campfires. Well, what's actually happening there is a chemical reaction in which carbon from the wood is being oxidized and it's giving off heat. Now let's talk about a basic oxygen furnace, oxidizing the carbon. That's an example of a chemical reaction which gives off an enormous amount of heat. So in both of these cases, heat is released as either heat, sensible heat, which we'll define soon enough, or as light. So the kind of reactions that release energy are exothermic chemical reactions. And some examples, the energy is released when the fuel is burned, as seen on the previous slide, where carbon reacts with oxygen, the combustion of carbon, to produce CO2 plus heat. Likewise, when you oxidize silicon in hot metal in a BOF shop or a BOF, and it releases energy where silicon reacts with oxygen and forms silica in the slag phase, that gives off an enormous amount of heat as well. Likewise, energy is consumed in endothermic reactions. And a couple of examples of that would be, well, first one I have up on the slide is plants take in sunlight energy, okay, to produce carbohydrates. This is, as we all know, as photosynthesis. So what happens here is carbon dioxide gas reacts with water, and in the presence of sunlight, kind of like the catalyst or the energy that's required to get the reaction going, will then produce sugar and oxygen. And that carbon and sugar, or glucose, eventually becomes the carbon in wood and hot metal that we saw burning. Another example of endothermic reaction, which we'll talk soon enough next week, and I mentioned this earlier, is the solution loss reaction, where carbon reacts with CO2 to produce 2CO. The solution loss reaction is very endothermic. It takes away an enormous amount of heat from a process, which we need to spend to get in there in the first place. But the benefit of it is it regenerates or rejuvenates the reducing gas. It's almost like recycling reducing gas. We'll talk more about that next week. However, the downfall is it is highly endothermic. Hence its name, the endothermic gasification of carbon. Now, the first and second laws of thermodynamics was actually the discussion question of this week. When we first constructed this program, Todd and I and the builder, Rich, we felt that stick to one question for discussion topic. And I tell you, there were many questions that I could have asked on this particular subject, but I thought that kind of having a discussion on what the laws of on the first two laws of thermodynamics was definitely a good question. And the discussions that I've seen so far, I'm really amazed of the level of knowledge that most of you have on the first and second law of thermodynamics. So the first law, as most of us kind of understands it as, energy cannot be created or destroyed, transformed from one form to another. Okay, so the first law of thermodynamics is a version of the law of conservation of energy that we've learned back in high school physics. And the law of conservation of energy can be stated: the energy of an isolated system is constant, meaning that the universe has a constant amount, a finite amount, a constant amount of energy, and it cannot be created or destroyed. It could be transformed from one form to another. The second law, and is spending a considerable amount of my education years studying thermodynamics and quantum mechanics, the second law is what really intrigues me. And that is, all natural events are governed by the desire for a decrease in energy on one hand and an increase in entropy on the other. We'll talk a bit about entropy in a minute, of what that term means. But for the scope of this course, and in fact the scope of this program, understanding these from a conceptual level and is sufficient and is all that's really needed. So the second law of thermodynamics, what it's saying is, if I'm going to transform energy from one form to another, in the process of that transformation, I can't transform 100% of that energy without losing it to the surroundings. And as the energy gets lost to the surroundings, the entropy will increase. So it's saying that the entropy of the universe is increasing. And that's the second law of thermodynamics. So the first law of thermodynamics says you only get what you put in, I'm speaking in simple terms. And the second law of thermodynamics is saying, no, wait a minute, you're actually, you're always going to lose. and that's what the second law is. The entropy of the universe is increasing. There's actually a third law, and that's another interesting law. And on that law, it states that a perfect crystal will have a constant entropy as it approaches absolute zero. So what does that mean? Well, it means that, in other words, it is impossible to reach absolute zero, and absolute zero is minus 273 Kelvin, in a or absolute zero Kelvin. It's the same thing. In a finite number of steps. So as you're taking, as you're trying to lower the temperature of a substance or whatever have you, it is impossible to reach a state of absolute zero in a finite number of steps. And my understanding to that in simple terms is because as you're approaching absolute zero and the entropy is approaching a constant, then it's more difficult to drive that process as now entropy is no longer starting to increase. So there's no driving force for that to occur. Back in the days of Einstein and company and his fellow workers, when they were trying to determine heat capacities of specific materials at very low temperatures, they were able to get like about 15 degrees away from absolute zero, but not actually down to absolute zero. I just thought I'd add that on the side. So entropy, it's stated in the second law of thermodynamics, and the entropy of the universe is increasing. So what is entropy? So the best way to think of entropy is, you may have recalled this from high school and even in university for some of you that have taken technical courses or science courses. The best way to look at it is what happens when when you heat ice. Entropy is maximizing disorder. As entropy increases, disorder increases. So you take a mole of water, it's 18 grams of a block of ice, then you heat it, it will transform to a liquid, and ultimately it'll evolve as a gas and occupy 22.4 liters. So that's an example of entropy where the disorder of the system is actually, or it's becoming more disordered. So the entropy is increasing. There was actually a very good example in one of the discussion questions. I thought it was a really good one, where the gentleman said, you take a liquid and you put it in a freezer. It starts off at a value of entropy, or let's just say for argument's sake, a level of disorder. And then you're taking heat away from that water, and then ultimately that water freezes, and now you're left with ice, and it's more ordered state than it was originally in the liquid state. So in this case, the entropy is decreased. So how does the second law apply that the entropy is increasing? Now, I thought that was a great example because, well, for you to get that water liquid form to ice, you had to remove the heat away from the system, so the heat was actually lost to the surroundings. So although you've increased the entropy state of that liquid going to solid, you've actually increased entropy of the entire universe when you included surroundings and the heat that was removed into the surroundings. I thought that was a very good example. I thought to make note of that. So what are the different forms of heat? Well, for the scope of this course and this program, Um, two main sources of heat that we're going to be talking about. There's chemical heat. That's where the heat contained in the substance can be released during a chemical reaction, such as the oxidation of silicon. And and there's the sensible heat, where heat is given up by a body between two temperatures, and that's the sensible heat. There's no change in state. Heat travels from hot to cold, as you can see in this diagram, the hot slabs. So what is enthalpy? Well, enthalpy is what we're going to use to measure the the heat content of a substance. The units of it will be in either joules, calories, BTUs. Enthalpy changes when the temperature of a substance changes. So when you're going from temperature 1 to temperature 2, you're increasing the temperature. You're also increasing the enthalpy in that in that material. And the change in enthalpy is written as delta H, where for a case of a chemical reaction, it is the enthalpy of the products minus the enthalpy of the reactants, and that's the change in enthalpy. And that's what we have here. Now, enthalpy, being a thermodynamic quantity, is considered a state function, meaning that if you want to determine the change in enthalpy or the change in energy, then it's the after effects minus the before. So in this case here, it would be the enthalpy of the products minus the enthalpy of the reactants. So the final state minus the initial state. And that's what standard states is about. So all enthalpy changes are calculated based on standard state, which is 25 degrees C and 1 atmosphere pressure. Okay, and when heat is taken in, delta H is positive, and when heat is given off, delta H is negative. So in the case of burning wood, you would expect a negative delta H, and in the case of a solution loss reaction or photosynthesis, you would expect a positive delta H. Heat capacity is also used, and as we increase the temperature of a substance from one temperature to another, then that material would have increased its enthalpy, and the heat capacity is required to determine that calculation. So there's a list of tables as to what their substances are and what their phases are and the amount of energy per unit of mass required to increase the temperature by 1 degree. In the case of CO2 gas, then it's 0.84 joules per gram per degree. So let's move forward here to how we, we calculate standard enthalpies. And I'll make sure that you'll have both the PDF files as well as the recording of this session. So in this case here, the standard enthalpy change, right? The enthalpy change for a substance that is formed from its elements is the standard enthalpy of formation. And this is given by tables, which we'll talk about in a few minutes. So essentially, to determine the standard enthalpy of formation, such as the formation of water, it's taken the enthalpy of formation of H2O minus the enthalpy of formation of hydrogen plus the enthalpy formation of oxygen, the reactants. And and rule of thumb is the enthalpy of formation of elements is 0, so the delta H for pure elements is 0. And in this case here, you're left with the delta H of H2O is then equal to the delta H of the formation of the reaction, which you'll get this from the table, which we'll discuss shortly. This is the table here as an example. So for the case of the water, so the enthalpy of formation to form water, H2O, at 298 kelvins would be negative 242,000 kgs, I believe. Let's see here. That's right, kilojoules. So these tables are, again, in your book, and you want to refer to page 32 and 33. Okay, there's the enthalpies of formation for chemical reactions to determine the energies, and as well as the enthalpy increment equations for elements and compounds is on page 33, which you're going to use, and that's to determine the sensible heat. So more or less, you use tables at page 32, which is the enthalpies of formation at temperature T from elements at temperature T, to determine the chemical heat from a reaction, so the enthalpies of formation. And then the second table on page 33 is to determine the sensible heat of a substance, going from one temperature to another. And that should be this table here on page 33. And it usually is a linear formula as a function of temperature. So, so the enthalpy increment change equation would then be, like, for example, for carbon monoxide, would be 30.2 times the temperature minus 9100. Okay, so to develop these tables here for the enthalpy increment on page 33 is where heat capacities come into play. So, the delta H, so to calculate the enthalpy change for a process, the increment equation would be delta H is equal to the heat capacity multiplied by the change in temperature. And these tables have already been generated for us to be able to do mass and energy problems, which then we'll move to the first example. So, your car consumes 6 liters of octane per 100 kilometers. 1 liter of octane has a mass of 0.7 kilograms. Assuming the only products of combustion are carbon dioxide and water, how many normal cubic meters of carbon dioxide is released to the atmosphere on a 50-kilometer round trip? So I've kind of solved this question in a methodical way for your benefit. So the first step is you need a balancing equation. So by what is given, the chemical formula of octane, C8H18, reacts with oxygen. They say that it goes to CO2 and H2O. When you balance the equation, then you should get C8H18 plus 12, a half O2, goes to 8 CO2 plus 9 H2O. So by taking a look at the molar masses, you can see that you have 114 grams of octane, 32 grams of oxygen, 44 grams per mole of CO2, and 18 grams per mole of H2O. Putting in its stoichiometric coefficients would then give 114 grams of octane, 400 grams of oxygen, 352 grams of CO2, and 162 grams of H2O. So we start off by 2,100 grams. And how does that 2,100 grams come by? Well, it comes by the mass of octane for a 50-kilometer trip, right? 50 divided by 100, because we know that it's 6 liters for a 100-kilometer trip, multiplied by 6 liters times 0.7 kilograms per liter. And that gives you 2.1 kilograms or 2,100 grams. Then the mole weight of octane, excuse me, would be equal to 114 grams. And that would be 8 times 12 plus 18 times 1. And the mole weight of carbon dioxide would be 44 grams, and it's its molar mass of carbon dioxide, 12 plus 2 times 16. So the mole weight of carbon dioxide is 44 grams. So from the equation, 1 mole of octane, okay, will generate 8 moles of CO2 from the balanced reaction. So therefore, each 114 grams of octane will generate 352 grams of CO2, which is 8 times 44. So if that's the case, then the mass of CO2 generated would be 2.1 kilograms of octane multiplied by 352 divided by the 114. And that will give you 6.48 kilograms. So when you get these PDFs of this PDF file of this tutorial, it wouldn't be a bad idea just to go through it on your own time to better understand it. So the moles of CO2 generated would be 6,480 divided by 44 grams per mole, which is 147 moles. Or we could also express it as kilomoles, which is 6.48 divided by 44, or 0.147 kmoles. So it's up to you on how you want to express it. It's common to express it as kilomoles, but just multiply by 1,000 to get to moles. Volume of CO2 generated on a 50-kilometer trip then would be 0.147 kmol times 22.4 normal cubic meters per kilomole. That's, again, the gas rule that we talked about earlier, and now it's coming into play in doing this mass balance. And that will give you 3.3 normal cubic meters. So this trip will generate 3.3 normal cubic meters of greenhouse gas, or carbon dioxide. So let's move on to question 2, relevant to a blast furnace. Okay, so you inject natural gas into your blast furnace to supplement a shortage of coke. The chemical formula for natural gas is CH4. We'll assume 100% methane. And the amount of natural gas injected is 50 kilograms for every ton of hot metal that is produced. So how many normal cubic meters of natural gas per ton of hot metal at STP? Okay, so the questions being asked here is, how many normal cubic meters of natural gas per ton of hot metal does this represent at standard temperature and pressure? Okay, well, the moles of CH4 then is equal to 50 kilograms given by the body of the question, divided by 16 kilograms per mole, so it's 3.1 kilomoles per ton of hot metal. So the volume of which that will expel is 3.1 kilomoles multiplied by 22.4 normal cubic meters per kilomole, which is 69.4 normal cubic meters per ton of hot metal. What is the actual volume of natural gas injected per ton of hot metal if its temperature is 20 degrees Celsius and its pressure is 3 atmospheres? Well, apply the ideal gas law that we talked about in the gas phase, where PV is equal to nRT. And in this case, the volume is equal to, isolate for V, so the volume is equal to nRT divided by P. Put in your values. 3.1 kilomoles multiplied by the gas constant, 0.0820, multiplied by 273 plus 20 to get into kelvins, your temperature, and divided by 3 atmospheres to get 24.8 normal cubic meters per ton of hot metal. Excuse me. So in this part here, so because the lower part of the blast furnace is so reducing, there is not enough oxygen to burn methane to carbon dioxide and water. We'll talk more about this next week. So instead what happens is the methane molecule produces carbon monoxide and hydrogen. This is how we generate reducing gases, by injecting methane. So a balanced equation for the chemical reaction in the Tuer Raceway is CH4 reacts with oxygen to produce carbon monoxide and 2H2. So the number of moles of reducing gas are generated from 1 mole of natural gas would be 3. You have 1 mole of carbon monoxide and 2 moles of hydrogen. Okay, so calculate, let's move to question 3. Calculate the change in enthalpy when 1 ton of hematite, Fe2O3, is reduced to wustite, FeO, by hydrogen gas at 1100 degrees Kelvin. Repeat the above calculation using carbon monoxide as a reducing gas. So in part 1 of the question, we're now talking about chemical heat in form of a reaction where with hydrogen, FeO plus H2 goes to Fe plus H2O. And you can see here that you apply the table that we talked about on page 32. That is the enthalpies of formation at temperature T. And essentially you do the enthalpies of the products minus the change in enthalpies of the reactants. So for FeO and H2, because H2 is a pure element, its enthalpy will be 0, and that, it's products. So because the enthalpy of iron is 0, it's 0 because it's a pure element, and the enthalpy of H2O is minus 248. And then you put in the enthalpies for FeO, which is minus 265,000, and the enthalpy of hydrogen is 0. So you just apply the table, Appendix 5 on page 32 of your courseware. And that gives you 17,000 kilojoules per kilomole. So that's the enthalpy change for that reaction. So the enthalpy for 1 ton of FeO, which is 71.8 kilograms per kilomole, will then just be 1,000 kilograms divided by 71.8 kilogram per kilomole multiplied by the 17,000 that we have up here. It gives you 236 megajoules. And it's positive, meaning it's an endothermic reaction. So this reaction here, and this is key for next week's discussion, by doing reduction of wustite with hydrogen renders an endothermic reduction reaction where heat is required or taken from the process. In the case for carbon monoxide as the reducing gas, and you want to reduce wustite with carbon monoxide to metallic iron, and then what happens in this case is follow the exact same methodology, go to the enthalpies of formation table, and determine the change in enthalpy of the products minus the change in enthalpy of the reactants. And in this case here, it's negative 17,000 kilojoules per kilomole. And converting that enthalpy from 1 ton of FeO, that gives you a negative 236.7 megajoules. And it's an exothermic reaction. So by doing reduction with carbon monoxide of wustite to metallic iron, you actually are giving heat off to the process, which is a good thing. So there's 2 ways of how iron ore or wustite can get reduced through means of hydrogen reducing gas or means of carbon monoxide. One of them is an endothermic in the case for hydrogen, and the other is exothermic for the case of carbon monoxide. Well, in fact, there's benefits for hydrogen, although it is endothermic, in the fact that it's a very small gas molecule. Its diffusivity, its ability to diffuse into a pellet and reduce, is very high. So the kinetics of hydrogen for reduction is very quick, whereas for carbon monoxide is not as quick. So the balance between the two, both of those reducing gases together at some balance, acts as a very synergetic way, acts in a synergetic way. We'll talk more about that next week. So that then concludes the tutorial session for this week. And again, if I'm doing this correctly, I've recorded the session. I'll make sure that I will post a recording as well as the PDF of this tutorial. And I'll take any questions if there are any. I don't see any questions being posted. There's a question right here. Okay. Yeah, you could type it in if you don't mind. And I'll read your question. Same number of molecules. Okay, so the question I have here is trying to read it. 1 second. I am still not convinced about something you stated earlier in last week's up yet. If so, I'm not sure how to get it. Okay, last week's tutorial will be posted shortly. I will make sure that it gets posted. Sorry for the delay on that. We had some technicalities on last week's tutorial recording, some software issues. However, I believe that Todd has sent out the PDF file of last week's tutorial. I've also asked him to post it, and I hope that that he has done so. If not, we'll do so shortly. There's another question here about different types of atoms having the having different types, having the same number of molecules in a 1 liter container. Wouldn't their densities be different? Okay, well, that would only be if the so what it's saying, what the gas law is saying, is under a condition of standard temperature and pressure, if the temperature is 0 degrees and the pressure is 1 atmosphere, then a gas will exhibit, 1 mole of gas will occupy 4 liters of volume. And that's more or less what it's saying, and it's true for diatomic or ideal gases, and with that law or that rule, we've actually applied it to the some practical questions that we've just gone through. Okay, Robert, if you could send me the if you could send me your question by email, I could further elaborate on that. So if there's any more questions, I'll be more than happy to answer them. No more questions. So other than that, I I hope this tutorial was helpful. Again, I'll make sure you'll get access to the PDF files of this with solutions to the 3 problems that we've taken up, as well as the as the recordings. So with that, I'll conclude this evening's tutorial and have a good night. Thank you all.